Tonight's lecture is on structural engineering. The lecturer is Erkel Sr., a distant relative of mine, who is president of Erkel Greenfield. Has designed many of the major high-rises in Los Angeles. And just so you'll know, I know there's been a great tradition of lawyer bashing in the past in this, but given the fact that his hard work paid for my legal education, I know he would be very upset if anyone made fun of lawyers, given his deep respect for the profession. So, take it away, Dad.
Okay, I understand these sessions are rather informal, so we'll continue in that mode. If at any time you have a question, why, just speak up. We'll try to keep this thing in terms of what you want to know, rather than what I've prepared. I prepared a very sketchy outline, which you'll find on page 1. And we'll try to follow it in general. I did dictate some notes on the following pages so that you can read them at your leisure later on. We'll hope to cover most of this information in the time that we have. Basically, structural engineering is such a broad field that I decided to arbitrarily just confine it to high-rise structures or multi-story type work. And multi-story work is different in that it's generally type 1 construction. Those of you that don't realize or know what type 1 construction is, that's either structural steel or concrete with a maximum fireproofing requirements. Most of the buildings in the downtown area, in fact almost all of them, are type 1 construction. The buildings that we'll confine our discussion to will be mostly office buildings and residence-type building, condominium apartments, and hotels. Special buildings such as hospitals, bridges, that sort of construction will not be addressed in this discussion. The codes that you follow for multi-story work are the three major codes: the Los Angeles City Code, the Uniform Building Code, and the Los Angeles County Code. Now, for government work, or state or city, there are, not city, but federal or state, they have special codes. The state has the various title sections, Title 21, Title 22, and 23. But we won't be getting into that because most of the buildings we'll be talking about are private enterprise. I understand most of you are going to be in the development business. Is that your objective? Okay, well, it's not absolutely essential that you understand or know the details of structural engineering or any of the engineering disciplines, but it is good to know what might be required or might come up during various conversations and various problems during the development of a project. First of all, you have to address the idea of loading. Now, loading falls into various categories. The dead load or the gravity loads of a building, that's pretty basic. Everybody recognizes that your columns and footings and beams and girders, shear walls, and seismic resistivity of the building has to basically take care of the gravity load situation in a building. Gravity loads are easy to figure because you know exactly what you put into the building, so you can determine the weight. Live loading, such as furniture and people, equipment, is pretty much defined by code. You don't have to guess at that. Now, one thing that may come up is that as a manager or a developer, you may want to increase the live loading of an office building. We try to, in our office, we try to let the client know what the incremental additive cost would be live load to a 100-pound live load. Now, what does that mean? The normal code requirement, say for an office building, is 50 pounds per square foot. But on top of that, you have to add a 20-pound partition load. So you really have a 70-pound live load that you're putting onto the floor system. The added 30 pounds doesn't really add that much to the cost of the building, and it does prevent a lot of problems during leasing periods. And we make a pretty good living just going in and checking floors and strengthening beams and so on in buildings that have been designed for just 50-pound loading. Yes?
This is 50 pounds per
Square foot.
square foot.
Yeah. That's a pretty good load. It's very difficult to attain 50 pounds. You pack people in an elevator, as many people as you get in there, and it won't be 50 pounds per square foot. So, but that's the requirement of the code, and every building every office building is designed for that. However, as I say, in addition to that, you have to allow for partitions, and that's a general loading of 20 pounds per square foot. But as I say, we get calls all the time is that a new tenant is moving into a building and he wants to put one of these mechanical filing machines, which are quite heavy, or they want to build or develop a library in one of their offices, which of course the bookcases and the books are quite heavy. With computers, these office buildings utilize and store a lot of paper. Paper weighs quite a bit. So there are problems that come up where we're asked to come in and check the floor loading. With a 100-pound live loading, you can generally eliminate a lot of the problems. There are certain things that you can't eliminate. You have to check it out. But that's one thing that may come up during your work as a developer or a manager of a major project.
Okay, yes, back there.
What do you think you're increasing the load, you're making it so that someone could have more weight, weigh the objects on their floor?
Yeah.
So you are, because of that, you're adding more steel, you're adding...
Yeah, the floor system would have to be increased slightly to accommodate this added load. Instead of an 18-inch beam that weighs 43 pounds, you may have to use an 18-inch beam that weighs 45 pounds. Because there would be an added amount of steel for the 100-pound live load that you would have to accommodate in your...
So older buildings that are already built that are only up to 50 pounds, they may have problems.
Well, even a lot of the newer buildings, the developer feels that he wants to save as much money as he can, so he doesn't add the 30 pounds live load. So I'm just saying that we try to educate our client to adding that extra load because it does prevent future problems. Yes?
What kind of occupancy problems are related to that weight is? If they go from, say, office use to what, public assembly, they're
Well,
a
no.
big step in load.
Yeah, public assembly is 100 pounds. Now, if it's not designed into the building, like this room here would be considered public assembly. And they probably didn't, well, maybe they did, I don't know. It depends on the design procedure prior to construction. But if this office, Lily Code, wanted to say this room is going to be for public assembly, they would have to bring the engineer back into the picture and check the room, the floor system, for the 100-pound live load.
So that, as a developer, that'd be one advantage of going to 100 pounds. You're
Yeah.
free to make big conference rooms without retrofitting.
Or file rooms. File rooms are always a problem. You got a new tenant, and he's in the paper business. I mean, he's got a lot of paper that he's going to be manipulating. So there's always a lot of files, a lot of paper storage, a lot of computers. And so there are areas that become concentrated with heavy loads, and they have to be checked out. Yes?
Knowing that obviously the upside there is more flexibility to carry more greater weight, but what about the downside in regards to the additive steel costs.
Well, that is the downside.
But how much more are we talking? Are we
Yeah.
talking proportional? I mean,
It's
substantially
probably,
more.
compared to the total cost of the project, it's probably less than 0.1%. So you're not talking about a lot of money, but, it's always crucial during a development period to stick to the budget. In fact, to reduce costs wherever you can. That's always, I've never in my 40 years ever experienced a project that didn't have a budget problem. And of course, the first thing they want to attack is the structural engineer. They want to be sure that he doesn't have too much in the building. And it's a fair thing, because the engineer's position is basically to do the job with the least amount of cost. So it's not out of line to try to accommodate the budget by reducing cost. Other areas of cost, of course, the big ones are architecture, just a special ceiling treatment. Decision between one or another could be maybe $2 a square foot. And steel, if you add 1 pound of steel per square foot in a building, if steel goes for, say, $1,200 a ton, you can figure out that the 1 pound doesn't amount to a lot of money. And that's a lot of steel. Straight to the building. Normally, a building like this one probably runs about 25, 26. Well, this is a fairly tall building, probably around 30 pounds per square foot.
Do you have figures for schematic design of how many pounds per square foot you would estimate a building is going to take? Somebody comes and wants a 24-story steel frame, high-rise. Can you tell them, X pounds per square foot per floor? Schematic design right off the bat.
Yeah, we have a pretty good library of information. Over the years, we've developed steel tonnage for a given building, depending on the number of stories, and the column spacing. The column spacing is very important. I mean, it's a factor that increases the tonnage. The longer the spans, the more tonnage. So we're able to develop a tonnage or poundage per square foot quite readily once we have some schematic drawings developed by an architect.
Mr.
Yes.
Have you found that, say, as there's been a bit of a modernization in construction techniques, you're finding alternative methods for more efficiently producing these types of steel structures? I mean, Dave mentioned that there was some kind of a tubular system design that they've come up with to, instead of going for the central spire type traditional approach, they're using a different.
Yeah.
Has
Well,
there been a lot of
we're going to
changes?
get into that a little bit. There are, for taller buildings, there are methods of not necessarily more efficient. It's probably the only way they could build a building that tall. As an example, the Library Square, the first interstate tower, which I guess is 72 stories or something like that. It's got a double tube section. Now, a tube section means that your columns are spaced relatively close together, like 7 or 8 feet on center, around the perimeter of the building. And then around the core, they have another tubular section, development of columns, pattern of columns. And these two towers of tubes, in a way, interact and give you the proper lateral.
But you're not seeing too many big changes in the way that it's being done.
Well, no, it's just that as you get into a taller building, especially in an earthquake area such as this, you have to develop other methods. When I say other methods, you got a tubular construction is nothing more than rigid frame construction, which is very traditional, very old, where the columns are close together. And a good example of this would be Erkel towers. They have columns, I think they're 8 or 10 feet on center on the perimeter of the building. Then on the second floor, they have a huge girder that picks up, I think it's every, two out of 4 columns. The first and fourth column go all the way down, and then the 2 columns are supported by a girder, a spandrel girder on the first level. But In order to, well, we're into wind loads and seismic winds, we'll talk about it a little bit. In order to take the lateral force of a multi-story building, you have to have beam to column connections that are called rigid connections. I've made a couple of sketches on the second or third page that show various methods of developing moment connections. Now, you need a certain number of those to resist the lateral force of, say, wind and or seismic forces. There's no other way. There are other ways, such as cross bracing or shear wall. But in a tall building like First Interstate, you have to have that kind of a framing system to develop the lateral restraint for seismic. Our office did the first First Interstate building, which is 62 stories, and we used a double or a three-dimensional rigid frame. And we didn't. It's not called tubular. The columns are pretty well spaced, around 28 or 30 feet out of center, but they go in both directions. Columns get pretty huge. At the lower levels, they're actually boxed columns. Billets of steel, and it's 5 inches thick, about 30 or 36 inches in the lateral dimension, and they're continuously welded. So we developed huge columns to take the lateral force that's applied to the building. So I don't know if that answers your question or not, but there are, gravity. There's nothing new about gravity, so you have to address that problem in a traditional way. Earthquakes, although it's a recent phenomenon, when I say recent, it's been going on for thousands, maybe millions of years, but we've only been recording earthquakes for maybe the last 100 or 150 years. So our database for earthquake knowledge is rather limited. And in fact, we have very little information on what they call near-field seismic excitations. That is to say, oscillographs that have been taken near the source of an earthquake. This is important because, potentially every building has this kind of a problem associated with it. But what we've done at my alma mater at Caltech, they've developed synthetic earthquakes, which incorporate all the bad features of earthquakes, and they've mathematically developed these oscillograms that we actually use instead of real earthquakes. We use these imagined or synthetic earthquakes to design our structures. The 62-story building, we used 11 different earthquakes. We pumped them into the computer mathematically. We developed a model of the structure, and using time history methods, that means every second we develop a motion at the base of the building, both acceleration and displacement. And the effect of that movement is transferred into the building a second at a time. So over a period of time, like during the duration of the earthquake, we developed a total lateral picture of how these forces affect the building. Now, we're concerned, of course, for the building not to collapse. I mean, that's our basic goal. But more than that, we don't want the building to exhibit detrimental considerations, like if the floor-to-floor displacement is more than 3/4 of an inch or 7/10 of an inch or 8/10 of an inch, there is enough tolerance in the glass and these glass panels to sustain that kind of a motion. As soon as you get into the 1 inch or 1.5 inches, you're going to get some glass breakage. So what we try to do in all these earthquakes that we've introduced into the building is make sure that the floor-to-floor displacement is, say, less than 1 inch or less than 8/10 of an inch, whatever criteria you want to set up. And what that does for you is it says, well, assuming that you've developed the right family of earthquakes as a design criterion, and future earthquakes fall within that parameter or that family of earthquakes, you're not going to get any serious damage to your building. And this is our primary concern, not primary, but it's certainly an economic concern, that you don't want to have to go in after an earthquake and spend several $1 million refurbishing the building. So that's one of the considerations that we use when designing a project such as a multi-story building. We make sure that the building doesn't deform more than what the partitions or the exterior window wall or the wall panels can tolerate as a lateral movement. The other consideration, of course, is over a long period of time, you're bound to experience very high magnitude earthquakes. During those conditions, you want to be sure that the building does not collapse. We develop, we've designed most of these buildings in the downtown area are designed to withstand certain earthquakes that have an 8 or an 8.5 magnitude. Incidentally, magnitude is a, yes?
I was wondering, what's the probability when you design things, statistical probability of some, a successful building being structurally sound? Is it 99.9? There must be some kind of measure.
Well, for one thing, there's no such thing as an earthquake-proof building, because we haven't experienced all the earthquakes that we're ever going to experience. But what we do is we say the magnitude of an earthquake is related to the causative fault. For example, the Englewood-Newport fault is a moderate-sized fault. It did generate the 1933 Long Beach earthquake, which was very destructive. It was about a 6.7 or 7.0, I can't remember which, but it's probably the maximum earthquake that fault can generate. The San Andreas fault, runs for about 1,000 miles, maybe more. It's capable of generating an 8.5, but you have to have some very special conditions for that to occur. And not only that, the rupture at the fault has to be near a major metropolis in order for it to be a destructive quake. If it happens in the middle of nowhere, well, it's bad, but it didn't kill anybody. So if it's going to happen, that's where we want it to happen. But your question is, what's the probability of experiencing an earthquake during the life of a building? We make a two-tier assumption. One is that we say, well, in this area, the downtown area of LA, or most of the area of LA, we have a lot of faults like not San Andreas, but the Englewood-Newport, the Malibu fault, the Whittier fault. These are all capable of generating a 6 or a 6.5 earthquake. So we say, okay, that's the kind of earthquake that's most probable for this building. So we design to withstand that very, in a very restrictive manner. Then we say, well, we have old San Andreas out there that's capable of generating an 8.2 or even an 8.5. So we say that's also a consideration. However, the San Andreas fault is about 43 miles away from the downtown area. So we take an attenuating factor, which is a reduction. We assume the earthquake happens at the lowest or at the closest point on the San Andreas fault. And then we use an attenuating factor to design the structure. Now, this is a very common way of designing high-rise buildings. I would presume we initiated that type of design on the 62-story building. And I think all the buildings subsequent to that are designed in a similar two-tier earthquake manner. So to answer your question, I think we're pretty sure that we've covered the ground, but we can't, actually, the good Lord may present us with a 9.0, and, you know, all bets are off. But you know, the San Francisco earthquake that we experienced just recently was a pretty good jolt, and the buildings in the downtown area, especially the modern buildings, withstood the earthquake very well. Our office was commissioned to look at all the First Interstate property. And the only property that suffered damage up there were the older ones, the unreinforced masonry. Buildings that were built 20, 30 years ago. The newer buildings came to be fine, which is a way of saying that what we're doing is probably on the right track. We haven't arrived yet. I think every time we experience a bad earthquake, we learn something new. We learn, you know, to design double-deck freeways a little bit differently. And quite a bit. That was a very terrible thing to happen. Yes.
I can understand that you're engineering your building so that your building will stand up. Do you consider that buildings nearby might hit your building?
Well,
The older buildings?
yeah, no, we don't consider that. I think buildings very seldom fall on each other. I really can't remember any time. They usually, when they crumble, or when they do experience an earthquake they can't handle, it usually kind of falls down within itself. However, it is a consideration. Just as an aside, when the first interstate fire occurred, I was watching that thing in horror, and I was wondering what would happen if the steel in that building did melt, and that tower would have fallen over, and it's tall enough so it would have collided with other buildings. But generally, you don't take that into consideration. The main effort of a structural engineer or anybody connected with a major building is to make sure that doesn't happen. You know, your objective is not what happens when the building falls over or another building falls into you. It's just make sure these things don't happen. Use the best technology you know how. But anyway, that's yes.
Are you familiar with that new technology that I think the Japanese developed, putting the buildings on rollers, and they give a 4-foot leeway in each direction of the building so it can move?
Yes. Yeah, in fact, it's not only Japanese, but it's been developed in Canada and in this country to a large extent. The flexible base concept, it's based on the fact that if you could provide rollers under a building, the earth could move and not introduce any lateral forces theoretically into the building. It's a good theory, but you know, during an earthquake, you can get as much as 10 feet of displacement. If you get that kind of displacement, wouldn't be, you know, your building could be rolling down the street. So you have to have some constraint, even with a flexible base. So when you get into that situation, you've got to assume that under certain conditions that building is still going to take lateral forces, even though you have a flexible base. But yeah, it's an interesting concept, particularly for older buildings, existing buildings. If you can jack the building up and put a flexible base under the main columns, you can then reduce the effect of lateral forces. And a lot of these older buildings are not designed to take the total seismic force. They just didn't know what the total forces would be. So this would be a way of upgrading a building without having to tear it down. Yes.
Yeah, it's not like a strange question. I was telling somebody at a house that was near the Wilshire corridor where there's quite a few high-rises. It was about 2 blocks away from some of the high-rises. He was very concerned that when the big one hit, that high-rise was going to tilt and come crashing down on his home. And I was just curious if a building is built and there is a major earthquake, Does the thing tilt? Does it go down? Does it go, I mean, what would be,
most-
I mean, if you had a fear, which, I mean.
Yeah. I don't think that's a proper fear. Most high-rise buildings are built with structural steel. Now, structural steel has an elastic stress strain curve, which is straight for a certain loading, and then it makes a yield point and then goes on horizontally to a point of failure, which is way down the line. In other words, steel will yield quite a bit, will actually elongate rather than pull apart. So in a major quake that has failed a beam to column connection, what happens is you get permanent deformation. You get a movement that doesn't move back. It's not completely elastic anymore. And it'll twist, but it won't pull apart. And so failure in a steel building is generally of that type. It's not one that collapses, falls down.
So even a worst case scenario, a real major earthquake
Yeah.
hits, the building is only set for 7 or 9 hits or
Yeah.
something like that, and it'll most likely just twist.
Yeah, most likely it'll just deform. Concrete buildings, that's another matter. Concrete will tend to accumulate fractures. It'll sustain earthquakes for a number of repetitive times, and the microfractures within the concrete will accumulate. They don't heal themselves. And then just a moderate earthquake can cause collapse in a reinforced concrete building. That's what we had in Mexico City. You had these shear walls that just collapsed, and the floors pancaked on top of each other. That's a very destructive type failure because there was no warning, no way to get out. I mean, it just killed a lot of people. And there are ways of treating or doing concrete buildings so that you do get an elastic condition, and that's called ductile design. That you put in quite a bit more steel, reinforcing steel, and you bundle them with a high or very low spacing of ties, so that the steel will yield during a maximum earthquake and not collapse. The concrete adheres to the steel reinforcing bars and will not fail. Olive View Hospital is a case where concrete columns failed because they weren't properly tied. The reinforcing wasn't properly tied. Well, I say properly, probably at the time they did it, the state of the art was such that they did what was required, but it wasn't, today we know better. We would do it a lot differently. Yes?
Would you feel safe in a building, let's say a high-rise condo in Century City, that would you feel safe in that's was built 30 years ago to earthquake standards of that date? I mean,
Well, I'd get the drawings and check them out.
What?
I'd check them out, I don't know. But I feel safe, I don't know. I just don't know how they were designed 30 years ago.
So you would actually go pull the drawings and check and see how?
Yeah. Yeah, I don't think that what we did 30 years ago is comparable with what we do today. I think since the 71 earthquake, we've learned a lot. We've changed the codes. We've gone into what we call dynamic analysis, which takes into account the period of vibration of the building as well as its mass. And we introduce a lot of different forces, and they're more realistic. Yes?
Couldn't your design, I mean, as good as it can be, can it kind of go to pot if your contractor, let's say, uses inferior materials or doesn't build it as to your plan and specifications?
Well, sure. I mean, the drawings are only drawings, that they have to be followed. But, be assured that we have inspectors. Not only our office engineers go out and look at the job, we have day-to-day inspection provided by testing laboratories. They check every every piece of steel that's brought to the job site to make sure they can, well, first of all, the steel company prepares shop drawings. We check the shop drawings to make sure they conform to our drawings. And then when they're actually delivered to the job site, we have inspectors that check to make sure that steel is the proper steel for that particular job. And then when they're put in place, the testing lab provides welding inspectors, high tensile bolt inspectors. It's constantly, continuously inspected. And I just don't think contractors today try to get away with anything. It costs them more to save a few bucks than it would be to do it right the first time. I don't think that's a concern. Yes?
How does this translate down to smaller buildings, stick and frame buildings? Is there as much earthquake problems?
Well, stick and frame, you mean like wood construction?
Wood.
Yeah. Well, wood construction has a high degree of flexibility. Nails connecting pieces of wood can deform quite a bit without collapse or failure. So I would say housing or type 5 construction, which is basically wood construction, has a very low failure rate. In all my experience, I haven't seen any real failures of houses or residential structures. It's been mostly buildings that have slid off their foundation because they weren't properly bolted to the foundation. It's that sort of failure. But the actual structure itself is pretty good. It may deform, but it won't fail. Yes?
I had another question. You said you were up in San Francisco and you saw glass unreinforced masonry buildings. Had any of those been retrofitted?
Yeah, they weren't collapsed. They were damaged. I didn't see any buildings. Well, there were buildings out there, not bank buildings. There were buildings that actually collapsed for a lot of different reasons. One was in the marina area where they had actually a quicksand or the soil was so unstable. We'll get into that too. But that type of soil during seismic excitation, it has to be sandy soil, cohesiveness soil. The water tends to rush up between the pores or particles of sand, and the sand particles become suspended, and you have little or no shear value, and it's like stepping into quicksand. So the bottom of a building that's sitting on that kind of a sandy material, if it should get into a quick condition, will actually sink and tilt over, and that's what happened in a lot of those buildings in that area. It had nothing to do with the structure. It was strictly a soil problem. Well, we've kind of drifted away from the from the outline, but I think we've covered the same ground, just in a different order. I was going to talk a little bit about most high-rise buildings have perimeter frame. In other words, the outside four, or whatever shape the building is, four sides of the building have columns that take the seismic load. And that's a normal design, probably usual design for multi-story work. As you get into the taller buildings, then you get into what we call tube construction. You introduce more columns, closer space. The lower levels, you have to put in jack girders or spandrel girders to pick up the columns. Otherwise, you have a cage of columns coming down to the lobby level, and it's just unattractive and very not functional. Yes?
Can you draw what these girders look like? I have a problem.
that is a typical plan of a high-rise building. Now, on a perimeter frame, you would have columns like this.
It would be the perimeter frame that would take on the load of the any seismic activity. It wouldn't be the internal frame.
No, the interior, the core area,
Yeah.
like this, would have virtually no seismic capacity. It'd just be carrying vertical load, gravity load. But these columns would be fairly closely spaced, but they're all moment connections. This is what we've shown in that second or third page. Now, any tendency to move in this direction would be resisted by the beam to column connection. I mean, that is a fixed connection, and you would have a beam going into a column. It's a wide flange column. And this beam would be fixed to the column, and there would be a tendency for the column, for the beam to take, this is very exaggerated, but the column would go like this. In other words, the column stiffness would create a stability to your building. It would tend to absorb whatever tendency to move there is. Incidentally, an earthquake generates vibration in the ground. The vibration is a form of energy that is picked up into the building. And the stiffer the building, like if you go to a shear wall type building or a brace type building, it's a lot stiffer than a moment condition, rigid frame condition. So you would actually have to use up a lot more energy in a rigid building than you would in a building like this. This building will tend to sway, but it won't collapse. So we take that into account in the design of a major high-rise building, what type of framing we want to use. Yes?
One of the interesting things was saying when he was in the Trans-America building in San Francisco, is the upper floors of the wind force is so bad that you could have the tables move and vibrate and, things fall off the desk. Structurally, what went wrong with that building that it felt that kind
This is
of...
the pyramid building?
Yeah.
The pyramid building?
Yeah.
Yeah, well, I don't think, a building has to move. If it doesn't move, it's going to collapse, it's going to fracture. So movement by itself is not a bad thing. It's how it handles the movement. One of the conditions we looked at in the 62-story First Interstate building was you get sort of a buggy whip effect. When the ground moves, your tower doesn't just simply sway, it goes into second and third phases of movement, like a buggy whip. And when you get into that kind of a condition, the top floor will actually accelerate, quite a bit. And what we try to do is make sure that the building moves generally in a single mode of movement. Now, in that building, we have about 5 feet of movement at the top during a heavy wind or seismic experience. And we try to hold the acceleration down to a point where people don't feel it. You can get panic just from acceleration. Won't fail, but people will think it's going to fail, and that's almost as bad if people start running out of the office rooms, trying to get into stairwells. So you try to reduce the panic condition by moderating the amount of acceleration that you can control. Yes?
When you do the tubular construction, there's another set of columns?
Well, this would be a tubular construction. Yeah, but then you could have the tube within the tube, and you'd have a similar set of columns around the core. And then you get into bundled tubes, and then there's...
So the one, you're not doing a real high one, you wouldn't you just would do less
Yeah,
follow-ups
I would
around the
say
perimeter.
30 stories or less, you'd probably go to a perimeter-type frame on your building and try to take everything out in the columns on the perimeter of the frame. Yes?
For a tall skyscraper that has a lot of movement at the top, when would you use, like a rotating weight at the top to counteract that? Do some buildings use that?
That's an interesting theory. I've never seen it used, but there is a theory that if you put a lot of weight at the top of the building, you'll reduce the amount of movement just by inertia forces. And but it's kind of a risky thing. Once all that weight starts to move, you have to have a lot of strength under that, between that weight and the foundation to resist that weight. So I think you're better off not artificially putting a lot of weight up there. I think you're
What would
better
cause
off.
somebody to go that route? Like the John Hancock Tower in Boston has huge weight at the top to counteract the movement from the wind. I'm just curious as to why they decided to go with that option instead.
You mean that was the method of correction, or?
Yeah.
I'm not aware of that. I thought they strengthened the core walls to reduce the amount of movement during wind. But I know there is a theory that by putting a lot of weight at the top of a building, and this is artificially, I mean, a tremendous amount of weight, that you can reduce the amount of lateral force or lateral movement. And I've never used
That comes with practice.
Yeah. Yes.
With the first interstate you were mentioning, 5 feet of movement at the top, is that like a typical wind, a 30 or 40 mile an hour wind, or is that a
Maximum wind, and it's like 2.5 feet in each direction. So you have a total sweep of 5 feet, and maybe even more under seismic conditions. But the acceleration is such that you really don't feel it. You can observe it by standing up there at the top of the building and looking at some fixed object, like the Hollywood sign or something like that, and you can see that you can sense the movement.
but it's slow enough that people wouldn't feel
Right.
it?
You keep the acceleration down to a point where it's not sensed by the people in the building. Well, there's another form of taking seismic out of building. We don't use it much here in LA, but in Chicago they've used these braced buildings, with these huge exterior braces, and this is very very acceptable in those areas. You don't have a seismic problem in Chicago or New York, but you do have large wind conditions. And these braces are very good for resisting wind loads and also reducing the amount of steel, because all the load is now going axially through the members. It's not being taken in bending. When you go into resisting lateral forces with bending, you have to spend more money for steel. So there is a good reason for going with brace bends. I remember years ago, when I was working for the old Carrera and Luckman firm, they sent me to New York. It was about the time they were doing away with the high-rise limitation. We had a limitation of 13 stories at one time in LA, and they were going to eliminate the 13-story requirement. So I went to New York, talked to various engineers to find out how they handled wind loads, taller than 13 stories. And they used a lot of knee braces. And I said, well, how do you design for a knee brace? How do you know how can you preconceive what the knee brace is going to do for you? He said, well, you really can't. He said, we just developed empirical data over a period of time, and we know how that affects a building, and we just use it. If it's not enough after the building is built, it's not that much of a problem to go in and put additional knee braces. in the frame. So this is the way they handled the problem in New York. Of course, this was before computers, digital computers, which allows you to make very difficult calculations in a short period of time. So we could actually determine what the forces are in a knee brace and how it affects the overall structure. Lattice bracing, I put that down, but I know of no building no major building that has lattice construction. Yes.
What is a knee brace?
Okay. I did as a little sketch in there of a knee brace, but let's say this is a column, and this is a beam goes into the column. Let's say you have a fixed condition, and if this is not sufficient, you can put in a knee brace. It's another beam that goes in at an angle and just allows you to take additional forces. It's just a way of stiffening this beam to column connection. As I say, I think we have a little sketch of one, but well, let me briefly touch on shear walls. Shear walls are just a concrete wall that goes between columns. And as you might visually understand, it provides stiffness in the plane of the wall. Any movement of the building would be resisted by this wall. And the wall, if you have enough of a wall and it goes all the way down, it will work as a shear resisting element. The problem with shear walls is that they're generally made of concrete, and once you introduce concrete shear walls, it's very difficult to make them work with any other type of lateral framing methods, such as a rigid frame. Rigid frame is more flexible, and in order for the rigid frame to work, it would have to move a certain number of inches, and if it moved that far, it would actually shear or crumble the shear wall. So they don't work too well together. You have to design them either one way or the other, either as a moment frame condition or a shear wall condition.
Could you explain moment versus shear?
Okay, now if you have a floor, you have a floor below that. Say this is the 9th floor, this is the 10th floor. And let's say there's a force up here, resisted by a force down here. There's a tendency for one floor to move relative to the other. In order to prevent that movement, you put in a column, which actually goes all the way down, and you put in girders between the columns. These girders are welded solidly to the column. Now, any tendency for this floor to move relative to the other is taken by fixity of the girder to the column. In other words, this column, if it tries to move in this direction, is going to be resisted by this girder that's fixed to the column in torsion. Shear walls you don't rely on the moment. You simply fill this area, this wall, with a concrete or steel shear wall. That's a solid wall that is built between the columns. And the wall itself has a inherent stiffness so that any tendency for this floor to move relative to this floor has to be has to go through this wall. Now what you do is you build a series of shear walls all the way down to the foundation so that any tendency or any resistance to floor-to-floor movement is actually delivered down to the foundation. I know that's not a good explanation, but it's, without going into mathematics, I don't know how else to explain it. The idea is that when you have a fixed condition, in order for the fixed condition to operate, you have to have a lateral force. If you didn't have a fixed condition, the whole thing would fall over, without any resistance. Shear walls are graphically very understandable. They're in place, and any tendency for the movement from one floor to the other will be taken by the shear walls. Okay, foundations. The most usual type of foundation is a spread footing type foundation. In other words, a column goes down to the ground and is taken by a pad of concrete, depending on the amount of load and the bearing pressure of the soil. It's an isolated footing. The soil conditions in the Los Angeles area, was compared to New York or Chicago or any of the cities back east. We don't have rock or a rock type base under our ground. We have an alluvium, which is basically sedimentation from billions of years of water and rivers running into the ocean. The sediment is basically clays and adobe and sandy loam, that sort of thing, which does not have a high bearing value. So the spread footings usually don't work too well on multi-story work. We have to either go into a mat type footing or a pile foundations. Of course, there are various types of piles. There's precast and drilled and belt caissons and so on. But what you try to do is get down low enough with your piles to accommodate the loads in the building column. In a 30-story building, for example, this column on the exterior wall may have as much as 3 million pounds of load. In order to take 3 million pounds on a footing that is only good for maybe 8,000 pounds per square foot, you have a huge footing. In fact, the footings would be so large that between the columns they would actually touch. And when they get to that condition, you might as well go to a mat foundation. A mat foundation is a solid slab, maybe 5 feet thick, under the tower, under the building. And in fact, that's what we did on the First Interstate Bank. We have a huge mat foundation that I think is around 5 feet, 5.5 feet. And it's such a tall, slender building that we decided to put perimeter caissons. Just draw a section. The ground level, this is the excavation. And we put in a 5-foot mat. The tower itself is like this. And at the perimeter of the tower, or of the mat, we put in maybe a 5 or 6 foot caisson. And these caissons were about 20 feet on center, and they do it completely around the mat. The purpose there was that in case there was any tendency to overturn during lateral forces, these caissons would act in tension and keep the building stable. And it's a very valid method of anchoring your building so that, especially in a tall, slender building where your aspect ratio is around 7 or 8. Aspect ratio is the height of the building divided by the width of the building. Yes.
So you're saying that the mat footing can be put on the alluvial soil?
Yeah, because you got so much area that even with a low bearing pressure, it can sustain the total weight of the building. Another little trick that's used, not trick, but a way of taking care of settlement is to try to make your excavation, you compute the weight of the soil that you remove out of the ground and try to make that approximately equivalent to the weight of the building. That way the soil at this level has the same bearing pressure after the building is built as it did before, because the weight that was here is taken out and replaced by the building and the mat. So the tendency to settle will be reduced. That's a big problem in this area is differential settlement. When you get into individual spread footings, there is a tendency for one footing to settle more than the other, which can cause a lot of grief after the building is built. You try to take those things into consideration during the design. But it's not always possible to do that. I mean, it's not always possible to anticipate exactly the amount of settlement that you might experience.
In this case, the foundation is dramatically larger than the building.
Well, we took it to the property line. Yeah, it was quite a bit larger than the building itself. The architects like to have a setback, and there is I'm not too familiar with it, but there is a limit to the amount of area you can build in a building as compared to the area of the site. I'm not sure what that ratio is, but they wanted to go up 60 stories, 62 stories, so in order to do so, they had to make a smaller cross-section, almost a needle-type building. Well, when you get into that shape of building, you have other problems. You have problems of overturning, and so in order to overcome that, we made sure that the mat foundation was securely anchored to the earth. And it solved a lot of problems. We had a lot of bearing problems. Soil bearing pressure was not really that great, so we had to accommodate it that way. Okay, we talked a lot about seismic considerations without defining magnitude. Everybody's familiar with magnitude. It's always after an earthquake, everybody wants to know what was the magnitude of that earthquake. Well, magnitude was developed by Charles Richter as a formula, and in effect, it's a measure of the total energy expended during an earthquake. When the fault fractures and moves suddenly, it unloads a lot of energy into the Earth's crust, which is transmitted horizontally in all directions until its effect is expended. He developed this way of, without getting into the mathematics, of defining the total energy as a ratio of, the seismic frequency, oscillograph conditions. But in effect, it's a measure of energy. And it's also a logarithmic. I don't know if you're familiar with logarithms, but that's a base 10 mathematical system. The difference between a 5 and a 6 is not, a 6 is not 1/5 more than 5. it's 10 times the energy. So every time you go up a notch in the magnitude scale, you're going up by a factor of 10. So that's why it's quite important whether it's a 6.4 or 6.5. Makes a lot of difference. And there's a common question that we always get. Well, now, is this building designed to withstand an 8.0 earthquake? Well, 8.0 simply tells you the total energy. It doesn't tell you anything about the duration or the frequency or the displacement or the acceleration. So it's really not a defining condition to earthquake design. And so there's no way to answer a question like that. We do use earthquakes that have magnitude 8 or 8.2 in the design criterion, but we don't, you can't say that this particular building can withstand all 8.2 earthquakes. We just try to make sure we get enough 8.2 earthquakes in the family of earthquakes that we select to design this building to resist, that all future earthquakes will fall within that parameter. Yes?
Do you ever do model mock-ups and family earthquakes? You're saying that type of design for all the high-rise buildings? Or?
Yeah, these are mathematical models. What we do is we develop a schematic of the structure, and we introduce the lateral forces caused by various earthquakes. And most of these earthquakes, as I explained before, are synthetic earthquakes. And but they do exhibit the qualities that you see in real earthquakes. But we have a whole book of them, and so we're able to pick and choose which earthquake we want to pump into this building. So on a major building, we'll pump in as many as 10 or 12 earthquakes. And they're, the types of earthquakes that we use have enough of a distinctive quality that we assume future earthquakes will fall within that category. And in general, this has been borne out to be true. We haven't experienced anything lately that's unusual or not predetermined.
But it's all a computer model numbering rather than physical modeling. You don't typically do physical modeling to evaluate.
We don't go into physics. That's universities do that a lot. But mathematical modeling is actually more accurate, I think, than physical modeling, because you have to take into account that you're not using the same magnitude of structure in the model, and you have a very different condition. But mathematically, you can develop very exact stresses and strains in lateral drift and lateral movement of the building. And they're fairly, they're rigorous analysis. They're just very accurate. If you try to do it before computers, it'd take you a year and a day to run one analysis.
Yeah.
But now you can do it overnight. We just let the computer run, and the next morning we have the results of a particular earthquake. Yes?
How do you physically test the soundness of a building as you're building it, as you're going along or near the end or at certain points? How do you actually test it?
Well, we test the materials that go into the building, and we test the method of attaching materials to the building. But we don't make a load test on the building, if that's what you mean. However, there's a saying that if a building can live through the loads that are applied to a building during construction, it can survive anything. I don't know, if you see a building that's under construction, you'll notice they've got piles of chipboard, maybe 8 or 9 feet high, loaded on the floor. Well, chipboard weighs probably 110 pounds per foot. So 8 feet, you've got about 800 or 900 pounds sitting on the slab. And, it scares you to death. You go out to the job and you see piles of sand that they put on the floor. You see elevators, temporary elevators, they've hooked onto your building and they rack and wave. They got all kinds of loading conditions that you really never anticipated when you're designing the structure. But these are things that happen during construction, and you have a factor of safety, and you hope for the best. If anything does happen, the contractor's right there to fix it. So he makes sure that he's within, plausible limits when he's applying these excessive loads. Yes.
Pardon my digression here, but I was involved in two buildings almost identical in size. One, because of economics, they ended up putting more columns in versus another which had more clear span in it. And that was more expensive. And this day it eludes me why that would be, because it seemed to me that you're putting more steel into the building than more columns.
Yeah.
I don't know if that's a frequent occurrence. Would you explain that?
Well, I think I can. The closer you space column, within reason, 25 feet is probably as close as you want to space columns. But if you have a building that has a 25-foot span between columns, one that has a 40-foot span or 50-foot span, the amount of steel that you have to apply horizontally is quite a bit more. The column steel will probably be about the same because you're carrying the same weight of building. But the horizontal steel would be maybe 4 times as much. And then the other side of the coin is that you don't have as many columns to take the lateral forces. So you have to apply, or you have to put more steel in the columns to accommodate that. So you do have a pretty good discrepancy or disparity between buildings with different column spacing. Column spacing is a very important element and for economy. And that might be something people will have to be looking into when you get into development. It's most structural engineers would give you a alternative tonnage. In other words, they'll say, okay, this is the shape of the building you want. This is a typical floor plan. If you have columns at 20-foot spacing, your tonnage will be so much. If you have columns at 30-foot spacing, it'll be so much. So you can get an incremental, fairly exact reading as to your steel costs. And then you decide for yourself whether it's worth the extra bucks for the flexibility of having larger column spacing. Column spacing is important to leasing agents. They have difficulty planning office space around columns. And if you ask them, they would like to have the building without any columns. I mean, maybe exterior columns, but interior columns, forget it. They would like to eliminate them. Obviously, you can't eliminate them entirely. So what you try to do is give the owner, the developer, or whoever an option to make a decision. Structurally, it doesn't make any. We can design the building properly, whether the spacing is 25 foot, column spacing 25 foot, or whether it's 30 or 40 or 50 foot. It can be handled, but it is an economic penalty, which at the end of the line, you have to decide. You as a developer have to decide whether it's worth that extra dough for more flexibility with your potential leasing clients. Yes.
And to follow up on that, is there a practical limit to the column spacing in concrete construction?
Yeah, concrete construction is tough. If you don't go to post-tension in concrete, I don't know whether you understand what that is, but that's a method of pouring your concrete beam, for example, and putting in cables. And after the concrete is set up, you tighten or put tension into the cables. And in effect, that allows you to go longer spans. But ignoring post-tensioning, I would say your maximum column span in an office building would be about 40 feet. Then you get into deep girders, which increase your floor-to-floor height because you got to get air ducts, and electrical, and lighting underneath your girders. So floor-to-floor height is important. you want to keep that as low as possible. And because, you know, in a 30-story building, every inch, you know, is 2.5 feet of volume. And that's an item of cost. That's a consideration. These are things you'll have to think about and ask for alternatives. You know, it's easy to do these things on paper. It's very difficult to change them once you're out there on the job site. Yes.
If you were designing a building in a geographical area where earthquakes were not a problem, what percentage of the construction cost could you subtract out for not needing the earthquake protection?
Well, that's a good question. You have wind, and so you will have to contend with a certain amount of lateral force. But I would say the earthquake factor, like when we do a dynamic analysis on a building, we usually add about 2 pounds, 2.5 pounds of steel per square foot to the building. So I would say, to answer your question, that's probably the penalty you're paying for being in a seismic area. And you would figure it out at $1,200 a ton what that amounts to.
What might that be percentage-wise? What does a building usually run at 10 pounds per square foot? Or, say a building like this.
Now, a building like this is probably closer to 28 pounds of steel.
So you're adding.
So if you're adding,
less
say,
than
3
10.
pounds, you've got about 1/10 or 10%.
As long as
9%.
we've sort of touched on concrete construction, say we were going to do a low-rise or mid-rise building, 5 to 10 stories or something, where is there some point where it would be more cost-effective to use concrete versus moment frame steel? Where does that
Yeah.
trade-off take place? Do you know? I've
Well,
seen 10, 12-story. People say it breaks at like 12 stories, you want to go steel.
We use about eight stories as a limit for concrete. You can go beyond that, but you get into some heavy costs in reinforcing steel and in actually placing the concrete around bundles of steel. So it has a point of no return. There is a 30 or 40-story building going up in Burbank. I guess it's all up now. It's concrete. I was really surprised. But I think they went out of their way to do that, and I think they got some good prices on concrete.
So concrete is definitely cheaper.
Concrete is a lot cheaper than steel. In fact, on a lot of these tall buildings now, they're using what they call super columns, which is a 6 foot, like a 6 foot diameter, maybe 5 foot or 7 foot diameter steel tube that they fill with high strength concrete. And that goes from the top of the building down to the foundation.
Is that cardboard too? Just start with the
Steel, structural steel. And the concrete and steel act together, and it's very effective.
No rebar inside?
Well, they may put some rebar, but basically it's, concrete is probably 1/10 of the cost of steel in terms of what you can do structurally. Concrete has a lot of problems, but its cost isn't one of them.
Even with all the rebar that has to go into concrete? I guess, well, obviously it's going to take more time to build a concrete one because they got to let each floor set long enough.
Concrete does take more time for construction. That's one of the factors you have to apply. In a typical high-rise building, say 20 stories, we figure there's about a 3-month differential between a concrete building and a structural steel building.
And how much total for framing?
Well, that's the total.
That's the difference.
That's the difference.
But
It would
what's
take
the-
you 3 months longer.
How long does it take to go up with the steel?
Well, steel goes up pretty fast, but then,
9 months versus 12?
no, steel goes up like in 3 months. And concrete, of course, steel goes up, but there's very little else going on. All your other trades have to follow the steel. Whereas concrete, it's a lot slower, but the other trades fill in. So it's not a complete comparison of total time for steel versus total time for concrete. But the overall time differential is about 3 months, and you can figure what that 3 months is worth, in rent, and getting your occupants in earlier, is paying off your construction loan that much quicker, and it's a computable cost differential. So the use of concrete, it has to be cheap enough to pay for all that and more. It can't be just a standoff. It's got to be more. And concrete is a very good product as far as cost is concerned. You shouldn't ignore it. Yes.
Well, when you get into the 30-story building you were talking about, what could possibly be the justification for going to that? I mean, it must have been some really involved design.
I really don't know the whole story. I do know one of the engineers that worked on it. Of course, he's a firm believer that concrete can be used for high-rise construction. I have an idea that there was a lot of pressure brought on the concrete industry to help pay for that particular project. So I can't believe it was cheaper. It took forever to get that building up.
But inherently, it's going to be a lot more risky with earthquake, too.
Yeah, well, of course, if you get into ductile design, you're putting in enough reinforcing so that it's going to act like a steel building.
Yeah.
So you're not taking that much risk as far as earthquakes are concerned. But you do have the problem when you bundle the steel and put in all these ties. The ties are like 2 inches on the center. And trying to get concrete between the reinforcing bars and the ties, you almost have to use a soup spoon to get it in, and it just takes forever to get those things done. And then the inspection is difficult. You got to watch make sure you don't have voids. So it's a tough proposition, but concrete is a lot cheaper. And there's always going to be a lot of pressure to try to make it work. Yes.
When you talk about the load bearing of the soil, when you use concrete, does the building wake every year so that you can't do that kind of design? Maybe you got to do something else.
Well, you can use a mat foundation because the pressure under a mat is very small because it covers such a large area. So yeah, you could still use a mat foundation, but you're right. If you have a concrete building, it weighs more. But there's always trade-offs. It weighs more, but weighing more means that it will resist wind loads more. Not resist, but it gives you more damping vibrations and so on.
I guess
Okay.
go ahead.
We had a scenario in here, one of the cases we had, of a floor slab of the beams in some areas not falling out at all, in other areas falling out too much. Assuming everything was done properly on the slab, pouring in concrete and everything, what would be your analysis of that? Of that happening? Does that happen frequently on the same floor levels of some areas falling out too much, other areas not falling out at all?
I don't understand the question.
Camber?
Camber of the beams?
Wasn't
Oh,
falling
the
out.
camber.
Yeah. Oh,
Now, what was your question about camber?
There was a floor slab being poured in, and the tenant was leasing space.
Yeah.
And so when they came in to do the redesign, or the architect designing of a marble flooring was going to stick up.
Right.
Okay, so some areas the beams didn't fall out at all in the camber, other areas they fell out too much. So he said it was going to wreck his design. But the contractors were going back and forth. But I looked even further. I would have to look into either the manufacture of the steel, maybe even the engineering. How do you feel about that?
Well, that's a problem because buildings with floor systems that interact, the interior beams and girders will deflect when you pour concrete. And then they're supported by other girders that will also deflect. So in the center of all this, you got a pretty large deflection. And the way to overcome this is, you can do it with camber. That's very tricky. It's a tremendous amount of work to try to figure out how much camber to put on each beam. You've got to make sure you get the right camber. The other is to forget the cambering and get a laser transit out there and just make sure that your concrete is level when you get through, which means that at the center of this thing, instead of having a 4-inch or a 3-inch thickness of concrete, you may have a 5-inch thickness of concrete. And you just take that into account when you're designing the floor system. But the top of the slab is then uniform, or is level. The problem, that happens is that you start putting in partitioning, and you have a big gap under the partition because the concrete slab has undulated. And in fact, it gets so bad sometimes you can throw a cat under the wall. And it's really not a happy situation. The tenants complain, the owners turn around and complain to the engineer, and everybody gets into the act. And it's a problem that's a real problem, and we have to face it every time we provide a client with specifications. We make sure that the slab is uniform, the surface of the slab is uniform. It's when they screed, screeding is when they trim off the top of the concrete. They go beam to beam. They don't go girder to girder or column to column. If they, if they would use a constant reference point, you wouldn't have the problem. And it's really a construction problem more than it is an engineering problem.
I didn't expect to say that differently.
Well, if there
So
was
you're
another
saying
way
they
of-
shoot everything first? If they shoot all the marks in with a laser transit first, you think that would solve that problem?
Oh, yeah. Well, they have to shoot the,
They have to shoot all the lines anyway.
while they'd have to shoot it while it's being placed, while the concrete's being laid. You got to make sure your concrete, in other words, you take a reference point on a column that isn't going to move vertically. Your girders and beams are going to move vertically. Your metal deck is going to move vertically. So you can't use that as a reference point. You have to use something that's fixed. And a column being fixed, you can measure from there and make sure that the top of the slab is uniform. But the engineer has to make sure that he takes into account the additional thickness of concrete, because that is added weight. The other alternative is to design each beam with a camber and hope that the contractor gets the beam in the right place, gets the beam not upside down, but right side up. I mean, there's so many ways to go wrong with cambering that, it can be done, but we found it better to put the onus on the contractor to make sure that he's got a laser transit out there and provides the owner with a level slab. Yes?
Around town, we see a lot of apartment buildings and stuff that have a type 3 or type 1 lower level for commercial use or garage, parking, whatever, concrete maybe, and then they have type 5 stacked on top of it for residential. Is that a really difficult structural problem where you're changing systems like that because of occupancy requirements or whatever, or does your office?
Yeah, well, it's difficult. Occupancy changes are not a problem. The type of construction might be a problem. You put a wood structure, like an apartment building, typical 3-story apartment building is built on top of a concrete subterranean garage. That's normal, and it's really no problem. You just have to make sure your concrete slab is thick enough to take point loads just anywhere, because you can't be sure that your point loads, your column loads, and so on are going to fall to the same point where the columns are in the garage.
Usually because car stall spacing doesn't.
Oh, yeah. In fact, under an office building, it's very difficult to accommodate column loads for a building and have them match up with the column loads required And, but where you have a condition like a light, type 5 construction on top of a parking garage, like an apartment building, you just make sure your flat slab or your slab is thick enough so that you can apply these.
So it's practically like the top slab is like almost a mat foundation for the Type 5 building.
Right. It's a two-way flat slab. Yes.
After you do your design, would there be anything that would bring you out to the site? You normally go out to the site?
All the
Structural-
time.
Do you? What do you go out there for?
Well, we go out at a minimum once a week,
Just to see that things are going
just to
correctly?
make sure that the design intent is being kept. Of course, we have inspectors that are there daily who report to us. But, no, we get out, our engineer, the guy that worked on the project, his responsibility is to go out and look at the job at least once a week during the structural phase of the construction. And then there are always problems on a job. So we get a call, and we have to run out to the job site and help solve the problem. And, no, that's a very integral part of our service is to follow the construction. Yes?
This shows my ignorance, but I've never understood how they put the high-rises up and get every beam correctly in place such that they all fit. Do they? And do they always number the beams, and do they ever mix up beams?
Oh, yeah.
About the process?
So there's a lot of horror stories. But basically, the steel company will provide us with what they call erection drawings, which show where they number all the beams, which show where each beam is supposed to be. And the numbers are actually on the physical beam. So when it comes out to the job site, they have a plan which shows where that particular numbered beam has to go. And no, it's very seldom to get the wrong beam in the right place, or vice versa. Yes.
On your project review, say as a developer, we want to go out to our projects and make comments on what the contractor's up to. Architects make a big effort to comment on design intent only and not comment on means and methods, and I would assume engineers have a similar problem there. Can you comment on the liability that we incur when we tell the contractor specifically how to do something?
Well, first of all, you never tell the contractor what to do.
But how
As
do
soon
you
as
tell
you
them
do-
that they're not doing?
Well, you let them know that there is a discrepancy between what he's doing and what's on the drawings. And then you follow it up with a memo or something to the architect or the developer or whoever is running the show. Usually a contractor will respond immediately. If you let him know there's a problem. But no, you can't tell a contractor to do something different. If he insists he's doing it right, then all you can do is write a memo or something which indicates that you don't agree.
Who's ultimately responsible if it fails, though? You, him, or the guy that did the shop drawing?
Well, my son will tell you, everybody gets sued, I mean, they go through the drawings and they pick off names. Even the landscape architect gets named. So, but who's ultimately responsible? Actually, the real blame is probably the inspection. The inspection should have caught it. The contractor obviously shouldn't have done it wrong. But once he's committed a mistake, then it should have been picked up by the inspector.
Who's the inspector?
What's that?
Who's the inspector?
Well,
City's not going to take it.
No, city. The Smith Emery people work for the owner, who really work for the engineer and architect.
So the consulting inspector.
Yeah. And they'll let us know if they see something wrong. And they're pretty good. They'll write it up as a failure to comply, and we, as soon as we get that kind of a report, we act on it. And we let the contractor know there's a problem. And generally, it's solved right then. He's not interested in trouble.
Well, when like trouble happens, like the Kansas City walkway that collapsed, and they said it was a a detail, I think, on a shop drawing where a rod was threaded all the way rather than solid.
Right.
Who ultimately picks that up? The guy that did the shop drawing, the contractor that installed it, the engineer that missed it on his shop drawing review, the architect?
Well, the
that missed
engineer
it?
got nailed. He was ultimately convicted for not doing his job properly. The problem there was it was customary in those areas. First of all, the engineer doesn't get much of a fee in those areas, and so they cut where they can. And the contractor picks up the load in terms of if there are shop drawings and he wants to change something, he goes in and changes it. And the engineer should, by professional practice, go out and look at the detail. And it's something that he should have seen. If he actually looked at it, he probably would have noticed that it's not right. And so anyway, that's the way that ball bounced. And, fortunately, it doesn't happen very often, but it doesn't have to happen very often to be a complete disaster. I don't know how many people were killed, but it ruined the lives of 3 or 4 engineers who were partners in that firm. And so it's a thing you have to be conscious of. And don't think for a minute we're not concerned. We're always, in the back of our mind, we always know there's a lawyer out there trying to get us. Isn't that right, Albie?
I got a great lawyer joke.
Mr. Erkel?
Yes.
What would you do if you have somebody out there compacting your site and they didn't quite do it right? And just that somebody didn't pick it up, and the foundation's going in, the steel's going in, and you start getting some major problems with differential setback.
Okay, that happens a lot, particularly in residential tract work. You have inspectors that go out and make soil compaction tests. However, they'll test here and then 50 feet away they'll test again, but nobody knows what happened between the 2 test areas. So if there is settlement, and let's say the residence or whatever it is starts to crack up, then there is a lawsuit, and I would think that the party they go after is the guy that did the compaction. Now, an engineer cannot be responsible for what he doesn't see. I mean, it's impossible to look at a tract of land and determine on the surface whether it's been compacted properly. But the testing lab, they can only do so much in terms of testing. They make in effect, a statistical average type thing. And if they didn't observe any problem, then and later on it was shown that there was a problem of compaction, then I think they go after the contractor and or the developer, whoever's got the most money. But it's something you got to be careful of, because it is a situation that's quite common in this area where we have a lot of adobe and clay materials that very difficult to compact. And then on top of that, adobe particularly will heave, will expand when it gets wet. So you can get a lot of problems that way. But this whole question of liability is a very difficult one. You don't have to have done something wrong to get sued. Everybody gets named in the action if there is a problem. And so what you try to do is make sure that you do your job well. And if there is a problem, you just make sure you've notified the proper people. If you're aware of a problem, you don't let it go. You don't make private deals with the contractor. You just let him know with a memo or something that the work is unacceptable. And what do? Well, if there is a problem before the project is finished, contractor can go out, excavate and recompact. I mean, there's that kind of a remedy before there's any damage. Now, he may feel that he's being asked to do something that was above and beyond his contract, and he may turn around and sue the owner or sue the engineer that forced him to do it. But those are lawsuits I think you can win. You know, if you're doing the right thing, you can generally win, or certainly keep the cost down low. It's when you've done something wrong and you try to hide it, or you assume it's going to go away. That's when you really get nailed. And that's something I tell the fellows in the office. The first thing when they find an error, either in the calculations or in the drawings or anything, is go out, get it fixed, whatever it costs. Let's face it now rather than later on. And I think most engineers, most offices operate that way.
Well, if you had your footings in place and some of your structural steel going up, and you start realizing the differential settlement going on at that point, would you be able to recompact underneath those footings, or would you beef up engineering-wise those footings, or do something that is counteractive?
Well, there's probably a lot of ways to fix a problem like that. So what you do is you evaluate it and do whatever is indicated. Yeah, you can get under a footing and remove the bad material and fill it up with lean mixed concrete. There's just a lot of ways of solving it. One of the most common problems is when a pile is driven or placed incorrectly. And it's pretty hard to move a pile on a job site. So what you have to do is take the condition that exists and then redesign a pile grouping that will accommodate the column load. You may add a pile or two into the group, but that's something that probably the least costly way of solving that kind of problem. And it does happen quite often. Yes.
On the last item on the agenda down there with the fire protection and the first interstate fire, could you give us maybe a little bit of insight on what you did what you found when you went into the building?
Yeah. I was saving that for last. I'm going to get a drink of water. Excuse me.
Now's the time to
Right.
Hi, Mom.
For all you that are watching this on video, you're all your...
You can do this instead of a roll.
That's right.
There you go. That's an idea. Save the paper.
Okay, before we get off into the fire discussion, are there any other questions on the seismic aspect of multi-story work? If not, we'll go right into the first interstate fire. Did you all see that movie, the Flaming, or the Towering Inferno? When I first saw that, I thought, God, this is Hollywood. They build something that just cannot happen. Where does all that fuel come from? Well, I got a call at 11:30 at night, the night of the fire. I said, don't bother to come down, but turn on channel 5. I turned it on. I couldn't believe what I was seeing. I mean, there was our building. I mean, and it just was on the 12th floor, but it was raging. And the way the fire escalated was that it broke the exterior lights of glass, leaped up a story or so, ignited the floor above. And I thought the thing was going to go up like a Roman candle. I thought it would just go all the way up the building. There was no way to stop it. And I guess it would have, except the fire department did a fantastic Well, I'll tell you, I really admire those guys. They had a program, I mean, not a program, but they had a way of fighting that fire that they had diagnosed before the fire. I guess these guys do their homework. And they had set up stations like on the 10th floor, and they were, with radios, they were sending guys up to see how far they could go with oxygen and so on, and they would keep track of everybody. Wouldn't let them in the area for more than a half hour at a time. They dropped people off on the roof and they came down. And they made an instant diagnosis that they would have to stop the fire on the 6th floor, I think it was. So they brought all their forces into that area and they just flooded the 16th floor. And they stopped the fire there. Didn't get beyond the 16th floor. But I just couldn't believe that there was that much to burn in an office building. You know, a steel and concrete office building. But we climbed up there the next morning, and the rubble was, you just couldn't believe the ashes. Everything burned, you know, anything that was plastic burned, ceiling material burned, the window wall, the aluminum window wall evaporated, and I don't know, tons of paper. You know, this is a computer age, so there was a lot of paper around. Computers ignited, filing cabinets burst open, and all the files burned. Carpeting, drapes, furniture, whatever could burn actually burned. Yes.
Isn't it all supposed to be fire rated, so it's not supposed to burn?
Well, when you're dealing with 2,000 degree fire, you know, almost anything. Well, anything can burn if you get it hot enough. But it was just appalling. And but the bright item was when we climbed up to the 12th floor and looked around. I could see the fireproofing on the steel was still intact. It was blackened, but the monocoat fireproofing that we had used was still in place. So we pried some of it off, and God, you could see the steel was still shiny, just like before they put the monocoat on. And so that was a relief. But you know, this is a 62-story building, and we wanted to be damn sure that there was no compromise in the structural integrity of the building. So immediately, like the following, this was on a Thursday, I believe. The following Monday, we had the Smith Emery people, the testing lab, with their metallurgists, and we started a program of Rockwell and Brunel hardness. That's a method of applying a deformation in the steel with a known force, and then measuring the deformation, the indentation. Now this doesn't sound like much, but it tells us what the yield point and the elastic limit and the modulus of elasticity of the steel is within a range of the accuracy. That was pretty good. Anyway, this we did on most of the columns and most of the major girders, and we found that the steel was still intact. And but that wasn't the end of it. We took off all the monocoat, all the fireproofing, and we took pieces of steel off the structure. We took them to the laboratory and performed elongation tests, which is a standard test for steel. In other words, you apply an increment of load stretching the steel, and you measure the elongation. Then you apply another increment of force, and you measure that elongation. And that gives you a pattern, usually a typical stress-strain pattern. I won't go into that, but that confirms that the steel is still viable, is still as good as it ever was. Okay, structural steel. Why didn't it get compromised in the fire? Well, structural steel is not a heat-treated material. It's a material that is an alloy with copper, chromium, carbon, and it has its great strength by virtue of its alloy, or its mixture of chemicals. And when it's formed in a billet form, And just prior to cooling completely, it's rolled into shapes. And it's allowed to cool normally, which means that when you reheat it and let it cool normally again, it's going to return to its natural state. There's no reliance on heat treatment or stress hardening. So steel can withstand high temperatures and still be useful after the fire. The thing you have to worry about is when the temperature of the steel rises, the stress that's in the steel, that is from the load of the building, can cause deformations. So steel could warp, it could deform, it could go out of shape, go out of plumb. So the physical, visual identification of a problem is readily visible. In this case, our steel members were so huge that there was virtually no we didn't see any deformation. We measured, and we couldn't measure any deformation. So we assumed that the stress-strain condition was not compromised by the heat. But then to verify all this, we did run these tests, this Fresnel and the other test. Anyway, we did run these tests and found that the steel characteristics were still intact. We took all the welds. Every weld in the building was ultrasonic. That's a method of determining whether there's any fractures or fissures in the welds. These are heavy welds, by the way. They're butt welds, huge butt welds. And we checked every major weld in the 4 floors that were ravaged by the fire. And I think we found 2 welds that had a slight fracture. But that may have been in the weld, after construction. I don't think it was caused by the fire, but it was insignificant, but we fixed it anyway. We took all the high-strength bolts, and we got calibrated wrenches, and we checked all the high-strength bolts for proper calibration, for proper compression, and they were all intact. The only thing we found as a problem, we had a metal deck system that had 3 inches of concrete, and the metal deck and the concrete work as a composite system. In other words, the metal deck acts as reinforcing for the concrete. And so we depend on bonding between the metal deck and the concrete. This is lightweight concrete. Although from the surface the concrete looked fine. But when they were trying to put in sprinkler systems, which they were doing at the time of the fire, they found that powdered material was coming, whenever they drilled in the soffit of the metal deck, they found a powdered material coming out, which meant that the concrete contact with the metal deck had pulverized, had calcinated. So as a result, we replaced the 4 floors. And in order to do that, without compromising the integrity of the building, we didn't want to take 4 floors of diaphragm out of the building, and then if an earthquake happened, we'd really be in tough shape. So we took a quarter of each floor at a time, staggered, and replaced them. Now, fortunately, this was Robertson Decking, and Robertson had discontinued making this particular type of deck, but we called them up and asked them if they could dig out their old dies, which they did. They were up in the Sacramento area. And so they replaced all the decking in an identical manner for us. So doing a quarter of the floor at a time, we replaced the 4 floors of concrete and decking. And as far as I'm concerned, the building is as good as it ever was. And the fireproofing, which was a non-asbestos fireproofing, by the way, we had learned back in '67 or '68, we did the VA hospital in Sawtell and one in La Jolla. And when I was back there at the time, this is 1967 or 68, they very curiously said we don't want to use any asbestos fireproofing in this structure. I said, well, that's okay. We generally don't anyway, but why do you say that? So they revealed to us for the first time there was some serious lawsuits regarding asbestos. At the time, I really didn't, I accepted their reasoning, but I didn't really think it was that much of a problem. Anyway, from then on, we've never used asbestos fireproofing, so this was a Monocoat, a WR Grace product, and it worked beautifully. The main structure of any building, of any Type 1 building, the main structure has to have 3 hours of fireproofing, and the secondary members, like the floor beams and so on, have to have 2 hours of fireproofing. The metal deck and concrete system has to be a 2-hour barrier, so the flames don't jump from one floor to the other through the metal deck or through the concrete. And everything worked fine. Everything worked according to the theory, according to the, that was kind of an interesting thing too. I've never thought about it much, but I often wondered if they really knew what they were doing with these fire tests. Because, every building has to conform to these fire restrictions. But I'll tell you, I'm a believer. I mean, they must really know what they're doing, because that 3-hour fireproofing on the main girders and columns just worked beautifully. In fact, all the fireproofing worked very adequately.
Was it something, the fact that the fire left out the window wall and then up through the window wall on the next floor, is that something that was anticipated, or was that kind of a shock?
Well, the fire department, the guys at the fire department, the heads of the fire marshal and so on, they say that's the way fire travels in the building. I'd never really thought of it that way, but the windows literally got blasted out. They were by the heat. And as soon as the window was no longer there, it just vaporized the mullions, the aluminum mullions, and just lapped up the floor above and the floor above that. It went up about 1.5 floors. And then that would blow out, and the fire would go in that way. It didn't go up the stairwells, or it didn't go up any of the openings in the ceiling. It went primarily through the outside of the building. And yeah, I guess that's the way it works. The fire barrier between floors, which is supposed to have a 2-hour rating, incidentally, they run actual tests, that is life-size tests of these fire restrictive elements. And whatever assembly you use has to have been tested. And it's kind of a pain in the neck, because sometimes what you want to use and what is economical has never been tested. But it's just like something that has. And, we get convinced that, well, it's probably as good, and so why not save the money? But the city is very, and the fire department is very stringent that you have to use an assemblage that has been tested. And so I'm satisfied that the system works. Yes?
Did they drench the 16th floor using sprinklers and standpipes, or did they have to bring in?
We didn't have sprinklers in the building. However, just prior to the fire, they were about 80% complete with a upgrading. They were putting in sprinklers, but they weren't functioning.
How'd they soak that floor?
They brought it in with hoses. Yeah, it was. When we got up to the 12th floor, there was about 1.5 inches of water, and the 13th floor and the 14th floor, it was just sopping. Everything was sopping wet. I don't know how they got the water up there. Of course, we have a tank, at the base of the building, just for that purpose. But from what I understand, that water was used up right away, and so they brought in water from the outside. These guys, I'll tell you, these firemen. Boy, I'm very impressed. They have about a 70-pound pack, you know, with their oxygen and hoses and everything, and they're running up and down these stairs like nothing. Just made me tired.